Taylor expansion of a function is an infinite sum of terms that express the value of a function around a certain point in terms of its derivative. In this infinite sum of terms, the order of the succeeding term is higher than the order or degree of the preceding term. In other words, f of x can be expressed as the infinite sum from n equals 0 to infinity of the nth derivative of f evaluated at a over n factorial times x minus a to the n. That's a lot. To unpack that, let's first figure out what we need to express f of x as. We want to express f of x as a power series, or the sum of terms with gradually increasing powers. In other words, a to the 0, not a to the 0, a naught plus a1 x1 plus a2 x squared plus a3 x cubed, on and on to infinity, or the sum from n equals 0 to infinity of a sub n times x to the power of n, where we want to describe a sub n as some expression relating the nth derivative of our function f. In order to do that, first we need to find what the first derivative of f of x is. The first derivative of f of x, or just the derivative of f of x, can be found using the power rule, because this is just a polynomial with exponents, not with variables in them. So derivative of constant is 0, then using the power rule we get plus a sub n plus 2a sub 2 x to the 1 plus 3a sub 3 x to the 3 plus 4a4 x to the 3 a sub 4 x to the 3, on and on to infinity. So just make sure to drop the exponents when applying the power rule. So what is the value of this derivative evaluated at 0? Well, all the terms with x in them just vanish, because 0 times anything is 0, and you're just adding 0 plus 0 plus 0. So you get, it's just 1 times a1, or a sub 1. Now, what is the double derivative of f of x? It's just the derivative of f prime of x. So using the power rule, we apply it again to get 0 plus 2a sub 2 plus 6a sub 3x plus 12a sub 4 x squared plus 20a sub 5 x cubed, on and on and on. So what is the value of this double derivative evaluated at x equals 0? Again, all of the terms with x in them vanish, so you're just left with the constant term, or 2a sub 2. Let's continue this. What is the triple derivative of f of x? We can apply the power rule once again. So the triple derivative of f of x equals 0 plus 6a sub 3 plus 24a sub 4x plus 60a5 x squared. And I'll stop there, but it continues infinitely. So what is the value of this triple derivative evaluated at x equals 0? Well, all the terms with x cancel out, so you're just left with the constant term 6a sub 3. Now let's generalize this to the nth derivative of f evaluated at 0. If you notice, it's just because of the power rule, just going to be n factorial, because the first one is 1 factorial, 2 factorial, 3 factorial, so it'll be n factorial times a to the n. Rearranging to get a to the n on one side, isolating a to the n, we just divide both sides by n factorial to get a to the n equals the nth derivative evaluated at 0 divided by n factorial. So now all that is left to do is to substitute this value of a to the n, which is in terms of the nth derivative of f evaluated at 0, and n into our summation. So that's just equal to the sum from n equals 0 to infinity of f, the nth derivative f, evaluated at 0, divided by n factorial times x to the n. And that almost looks like our Taylor expansion formula, except here, where there's a 0 in our Taylor expansion formula, there's an a, and then we're also missing this x minus a to the n. So where does that come from? Let's look at a specific function to figure that out. We'll be looking at e to the x, or the famous exponential function, whose derivative is famously its own derivative. So derivative of e to the x is e to the x, and I can continue that to infinity and only get e to the x. And I'm just rewriting our formula here so we can remember it. So that nth derivative of our function is always going to be e to the x. And I have a video explaining why the derivative of e to the x is e to the x. But just know that the nth derivative of our function is always going to be e to the x. And then evaluated at 0, that's just going to be e to the x, where x is equal to 0. So it's just going to be e to the 0, which is always going to be 1. So in other words, when we're trying to find the Taylor expansion of e to the x, it's just going to be the sum from n equals 0 to infinity of 1 over n factorial times x to the n, or x to the n over n factorial. So let's apply that formula to get our e to the x Taylor expansion. E to the x, starting from n equals 0, is going to be 1 over 0 factorial times x to the 0, or x to the 0 over 0 factorial. And you continue that pattern with n being 0, 1, 2, all the way to infinity to get this sum. And then I'm just going to simplify the x to the 0 to 1, and to 0 factorial to 1, so 1 divided by 1 is 1, plus x over 1 factorial, which is just x over 1, plus x squared over 2 factorial, which is just 2, plus x cubed over 3 factorial, which is just 6, on and on to infinity. And this is what you'll get if you search up Taylor expansion of e to the x. So how does this look graphically? Well, first, in real life, you can't sum up an infinite number of terms. Computation's limited. So I broke up these approximations to our constant approximation, our linear approximation, our quadratic approximation, and then our cubic approximation. So our constant approximation is just y equals 1. I broke off the polynomial there to get our first graph. Our second graph, I broke it up just after 1 plus x over 1 to get our linear approximation of e to the x. Then same thing to get my quadratic approximation of e to the x and my cubic approximation of e to the x. And you can see that as we get to higher and higher powers, we get more and more specific, and our approximation becomes better and better. So the problem is we can't compute this to infinity. So people in the real world have to choose where they want to cut off their computation. And notice that all these computations are very accurate at x equals 0, but the further and further you get from that center, or where your graph is centered, the worse and worse your approximation becomes. So with our quadratic and cubic approximations, this difference, this error, becomes smaller and smaller, but it's still there. So some people don't want to have to worry about, if we get this far from 0, our approximation's not going to be as good. So how can we figure out a way to get our approximation to, instead of being very good at 0, very good at a. So instead of centered at 0, centered at a. So to figure this out, let's take the very simple graph f of x equals x. Let's say we want to evaluate this function's value at x equals 4. But we want to find this value centered at 0, right? Because our Taylor expansions are going to be very good at approximating it at 0. How do we do this? Well, we can shift the entire graph to the left by a units to get our y value of x at 4 actually situated at x equals 0. So shifting the entire graph a units to the left to get our measurement at x equals 0, visualized here. So that's f of x equals x, and that's f of x equals x plus a. In this case, a equals 4, because we want to measure it at 4. Notice how now we can measure it at 0, and it's going to be the same value. And this is true for all functions. So, since f of x equals x plus a, f of x minus a is going to equal x. And so we can just substitute x minus a where we see any x. Replay that visual again. Our measurement is situated at x equals 0, but basically we're kind of measuring it at x equals a. It's kind of a cheating trick to get around it. Now we know that if we want to approximate the function f of x around a, or centered at a, all we need to do is replace f of x with f of x minus a. So I'm just writing down the Taylor approximation formula that we derived beforehand, and now replacing anywhere we see x with x minus a gives the sum from n equals 0 to infinity of the nth derivative of f evaluated at a divided by n factorial times x minus a to the n. Really quickly, the reason why it's the nth derivative of f evaluated at a and not 0 is because if you go back to how we derived it and replace those x's with x minus a's, you'll get the nth derivative evaluated at a. That's how one derives the formula for a Taylor expansion. Part 2 will cover how you can figure out the upper bound of your error if you take an nth degree polynomial approximation of f of x.